Let us continue exercise 1.3. 10th question. Let f be a function from x to y, be an invertible function. Show that f has unique inverse. So in this question we are going to use method of contradiction. What is method of contradiction? We will assume a wrong thing, we will get a wrong answer, so we change our assumption. Here we have to show that f has unique inverse. Let us assume that f has more than one inverse. So let us assume that f has two inverses, g1 and g2. By the definition of inverse function, if g is the inverse of f, we know that F composite G should be IY, or F composite G of Y is equal to Y for every Y belonging to capital Y. F composite G1 of Y is Y. Similarly, F composite G2 of Y is also Y, and it is true for all Y belonging to the codomain Y. Now let us equate these two. So F composite G1 of Y is equal to F composite G2 of Y, which can be written as F of G1 of Y is equal to F of G2 of Y. It is given that F is invertible. If F is invertible, we know that F should be a 1, 1 and onto function. So we say that F is 1, 1. The definition of 1, 1 function is, if f of x1 is equal to f of x2, then x1 must be equal to x2. This is the definition of 1, 1 function. Here we have f of g1 of y is equal to f of g2 of y. Using this definition, I can say that g1 of y is equal to g2 of y. That is, in place of x1 we have g1y, and in place of x2 we have g2y. So x1 is equal to x2. That implies g1 of y is equal to g2 of y. And it is true for every y belonging to the set y. Therefore, g1 must be equal to g2. Therefore, f has unique inverse. Question 11. Consider f as a function from 1 to 3. I am drawing the arrow diagram for this. 1, 2, 3 set to ABC set. And f of 1 is A, f of 2 is B, f of 3 is C. Find f inverse. Now this is f function. So from the arrow diagram we can very well say that it is a 1, 1 and onto function. It is 1, 1 because distinct elements have distinct images. It is onto because there is no leftover element in this set. Every element in the codomain has a pre-image. Therefore, it is an onto function. So I will write that f is 1, 1 and onto. Therefore, f is invertible. So f inverse will be therefore f inverse of A will be 1, f inverse of B will be 2, and f inverse of C will be 3. Now I am drawing the arrow diagram for f inverse function. So codomain becomes the domain and domain becomes the codomain. A's image is 1 under f inverse, B's image is 2, C's image is 3. Now if you notice, f inverse is also a 1, 1 and onto function. F inverse is also 1, 1 and onto. Therefore, F inverse is invertible. Let us write the inverse of this. You have to reverse it again. So F inverse will be, I am writing it in roster form, 1 comma A, 2 comma B, 3 comma C, which is same as the F function. Therefore, F inverse, the whole inverse, is equal to F itself. Question number 12. Let F be from x to y be an invertible function. Show that the inverse of F inverse is F. F is defined from x to y. Let G be a function defined from y to x. And we will assume that this is the inverse. Okay, let G from y to x be the inverse of F, because it is given that it is an invertible function. G is F inverse. And we know the definition. G composite F must be Ix and F composite G must be Iy. From this definition, we know that both are invertible functions, F and G. We know that G's inverse is F, F inverse is G. So I'll write that G inverse is F and F inverse will be G. I'm going to take inverse on both sides of this. So taking inverse on both sides, because G is also invertible function, we know. So let us take inverse on both sides. We get F inverse, the whole inverse, is equal to G inverse. But from this, I will mark this as 1. From 1, G inverse is F. Therefore, we get the result that F inverse, the whole inverse, is F itself. That is the result to be proved. Question 13. If F is a function from R to R, be given by F of x is equal to 3 minus x cube whole raised to 1 by 3. This is the function given. Then F composite F of x we have to find. F composite F of x is F of x, which is equal to F of, let us do the inner function, F of x is 3 minus x cube whole power 1 by 3. Again F has to be applied. Wherever we have x, we will substitute this. This is our x now. So 3 minus x is this, I said. And we have this cube and power 1 by 3. Let us simplify this expression. We can cancel 3's. So it becomes, distribute this minus sign, whole raised to 1 by 3. X cube power 1 by 3 becomes x, which is an identity function. So the answer is x itself. C subdivision is the correct answer. And from this answer we can say that F inverse is F. Now question number 14. Let F be from set R minus 4 by 3 to R. Be a function defined as F of x is equal to 4x divided by 3x plus 4. The inverse of F is the map G from range of F to R minus 4 by 3 given by. So we have to find the inverse function. Let F of x is equal to y. 4x divided by 3x plus 4 is y. Cross multiply. We have to find x, so collect x terms on one side. X is common. we get 4 minus 3y equals 4y. So that we can write x as a function of y. We will take this as g of y function, which is 4y by 4 minus 3y. Now we will check whether g is the inverse of f or not. We are going to use F composite and G composite f method. Let us find G composite f of x. G of f of x. G of f of x is 4x by 3x plus 4. Now let us use G definition. 4 times y. In place of y, I have to substitute 4x by 3x plus 4 divided by 4 minus 3 times, again y is 4x by 3x plus 4. Let's simplify this expression. 16x divided by 3x plus 4 and take LCM here in the denominator. LCM is 3x plus 4, which gives 12x plus 16 minus 12x. We can cancel the denominators, 3x plus 4. We get 16x divided by 16, which is x. We have proved that G composite f of x is x. Similarly, we are going to prove that F composite G of y is y. Now let us find F composite G of y, which is f of G of y. G of y function is 4y by 4 minus 3y. Now let us use f function. F function is 4x divided by 3x plus 4. 4 times x. Our x here is 4y by 4y divided by 4 minus 3y divided by 3x. X here is 4y divided by 4 minus 3y and plus 4. Let's simplify this expression. 16y divided by 4 minus 3y is the numerator, and take LCM for the denominator. 12y plus 16 minus 12y. y divided by 16 is y. So we have proved that G composite f of x is x and F composite G of y is y. Therefore f is invertible, we know, and f inverse is our G function. Therefore f inverse of y is G of y, which is equal to 4y divided by 4 minus 3y. The correct answer is B subdivision. Now we will do few important example sums. See page number 13, example 18. Show that if f from A to B and g from B to C are 1-1 functions, then G composite f from A to C is also a 1-1 function. Okay, we know the definition of 1-1 function. We assume that f of x1 is equal to f of x2, and we have to get the result that x1 is equal to x2. Then we conclude that f is a 1-1 function. This is the method which we use. Now in this question we have to prove that G composite f is a 1-1 function. So let us take G composite f of x1 is equal to G composite f of x2. Now we have to arrive at the result x1 is equal to x2. Now I am using the definition. G of f of x1 is equal to G of f of x2. Now it is given in the question that G is a 1-1 function. Therefore, if g of x1 is equal to g of x2, we say that x1 is equal to x2, no? Similarly, we write f of x1 is equal to f of x2. And this is the reason g is a 1-1 function. F is also a 1-1 function. So I can write that x1 is equal to x2. The reason is f is 1-1. And this is true for all elements x1, x2 taken from the set A. Therefore, G composite F is 1-1. Example 19, similar question but for onto. Show that if F from A to B, G function from B to C are onto, both are onto functions, then we have to show that G composite F is also an onto function. So this is set A, set B, set C, say. If I take an element X from set A, under F, f of x is y, say. Then under G function, g of y becomes z. G is an onto function. It is given in the question. So the definition of onto function is, for every z belonging to C set, there exists a pre-image y in B set under G function. Similarly, f is also an onto function. It is given in the question. Therefore, for every y belonging to B set, there exists a pre-image x belonging to A under F function. Therefore, this is our G composite F. Therefore, I can conclude that for every z belonging to C, there exists a pre-image x belonging to A under G composite F. Therefore, G composite F is also onto. If you consider G composite F function, this will become a 1-1 function only when F is 1-1. G need not be a 1-1 function. If G is not a 1-1 function also, G composite F will be a 1-1 function if F is a 1-1 function. It depends on F. Similarly, G composite F will be an onto function if G is an onto function. It doesn't depend upon F. F may be onto or may not be, but G has to be an onto function. Remember this point. Then example 24. Let Y set be set of all n squares such that n belongs to the natural number set n, which is a subset of n. That means I can say that in Y we have only perfect square natural numbers like 1, 4, 9, 16, etc. Okay, and the function f is from set n to Y as f of n is equal to n square. Let me show it using the arrow diagram. N has 1, 2, 3, 4, etc. And in Y set we have only perfect squares. 1 square, 2 square, 3 square, 4 square, etc. Show that f is invertible. So it has to be a 1-1 and onto function, and find the inverse of f. We can use 1-1 and onto method, or we can use G composite F and F composite G method. So let us take f of n as y. Usually we take f of x is equal to y, but here the definition has been given in terms of n. So instead of x we are using n, that's the only difference. The method is the same. So f of n is n square. Let us find n as a function of y in terms of y, root y. We don't write plus or minus sign here because n is a positive value because it belongs to n. We will take this as our g function, g of y as root y. Let us find g composite f of n, which is g of f of n equals g of f of n is n square, and g of n square will be root of n square, which is n. So we proved that g composite f of n is n. Now let us find f composite g of y, which is f of g of y, and g of y is root of y, and f function, square function, here it is. F of n is n square, therefore root y square. Root y square is y. Therefore g composite f is I n, and f composite g is I y. That means f is invertible, g is also invertible. So f inverse is g, g inverse is f. Now we have to write f inverse. So f inverse of y is equal to g of y, which is root y. Example 25, very important question. We had a similar question in exercise also. Put a star in your textbook for this question. It may be asked for 6 marks or for 4 marks also. F is a function defined from set n to r. The function f of x is given as 4x square plus 12x plus 15. Show that f from n to s, where s is the range of f, is invertible. Find inverse of f. Let us take f of x as y. 4x square plus 12x plus 15 is y. We have to find x as a function of y. So I am going to use completion of squares method. Or you may solve quadratic equation also. That minus b plus or minus root of b square minus 4ac by 2a formula also can be used. But completion of square method is easier. This is your a square term. So a will be 2x. And 2ab term is 12x. So plus sign it has, therefore plus. Divide this coefficient by 2 and divide by a term also. So it gives you 3. B is 3 here. Subtract b square term and plus 15 equals y. Now expand and check. See, a square term, 2ab term, 2 into 2x into 3, 12x, and b square term is 9. To cancel that we are writing minus 9. See, we get back the original equation. Okay, it's correct. Completion of squares we have done. Now by completion of squares, see, we have only one x term, so easy to find x. That's why we are completing the squares. So 2x plus 3 the whole square becomes y minus 6. Taking square root on both sides. We don't write plus or minus sign here because the left hand side is positive as x belongs to n. X is a positive natural number, so 2x plus 3 is also positive. So we cannot write plus or minus. I cannot equate it to a negative value. So no plus or minus sign in this. Now we can find x easily. which is root of y minus 6 minus 3 divided by 2. We will take this as our g function. Now we will calculate g composite f of x, which is g of f of x, and f of x is 4x squared plus 12x plus 15. This looks like a big expression, but it is easy. Let us use g definition. We get root of, our y here is 4x squared plus 12x plus 15, and we have minus 6 inside the square root, minus 3 divided by 2, root of 4x squared plus 12x, and 15 minus 6 is 9, and which is a perfect square. I can write this as 2x plus 3 the whole square. Square and square root could be cancelled. We get the answer x. Let us calculate f composite g of y. F of g of y. F of g of y function is root of y minus 6 minus 3 over 2. Let us substitute in f function. F function is 4x squared plus 12x plus 15, and our x is this now. 4 times x square is this square plus 12 times x. X is root of y minus 6 minus 3 by 2 and plus 15. This is also easy to simplify. Denominator is 2 square, which is 4. Cancel it. 12 divided by 2 becomes 6. Let us expand using the expansion of a minus b the whole square. A square minus 2ab term plus b square term, and distribute this 6. Y plus 3 and minus 18 plus 15 gives you minus 3. The answer is y. So we proved that g composite f of x is x, or I can write it as g composite f is in, and f composite g is is, because I have to show that it is invertible from n to s range of f. Therefore, f is invertible. Actually, both are invertible functions, f and g. And we have to write f inverse. F inverse of y is g of y, which is root of y minus 6 minus 3 divided by 2. And since we have root of y minus 6, y should be greater than or equal to 6. Otherwise, it will become a complex number. Let's do example 26. Here 3 functions are defined. F from n to n, g is also from n to n, h is from n to r. Defined as f of x is 2x, g of y function is 3y plus 4, and h of z function is sin z. For all x, y, z in n, show that h composite g composite f is equal to h composite g composite f. Okay, let us find the left hand side. H composite g composite f of x, which is equal to, the definition is h of g composite f of x, which is equal to h of g of f of x. We'll do the inner function. F of x is 2x, which is equal to h of g function has to be done now. 3 times y. Y is 2x plus 4, which is 6x plus 4. Let us calculate h function, which is sine z. Here z is 6x plus 4, so sine of 6x plus 4. This is the left hand side. Now let us calculate the right hand side. H composite g within brackets composite f of x. And this is H composite g of f of x, which is equal to H composite g. F of x is 2x, and this is H of g of 2x. And g of 2x will be 3 times 2x plus 4 using g function, which becomes 6x plus 4. And now use h function, which is sine of 6x plus 4. And both are equal. Therefore, H composite G composite F is equal to H composite G composite F. For all x it is true. This is nothing but the associative property of composition of functions.